NENOMATICA, where mathematics meets YouTube excellence. Welcome! In this lesson, we will build an intuitive cheat sheet of logarithm properties. We'll move step by step with visual rule cards and quick numeric examples. Let's begin with the two most fundamental facts. First, the logarithm of 1 is 0. Second, the logarithm of the base is 1. Next, product and quotient rules. Product turns into addition. Quotient turns into subtraction, and a reciprocal flips the sign. A quick example in base 10. Log 10 of 5 equals log 10 of 10 over 2, which is 1 minus log 10 of 2. Power rules. An exponent on the argument becomes a multiplier. An exponent on the base becomes a divisor. Together, m over p appears. The root versions are just fractional exponents. Change of base and reciprocity are the power tools for switching bases. The product of log b of a and log of b equals 1. And log base b of a equals log base c of a over log base c of b. Two lovely exponential identities. First, n equals a raised to log base of n. Second, x to the log base I of y equals y to the log base of x. We will carefully transform it, one line at a time, keeping the order identical to the worked solution. Step 1. Replace 1 over 5 by 5 to the power negative 1. Step 2. Use the power rule for logarithms. Log base 3 of 5 to the power negative 1 equals negative 1 times log base 3 of 5. That makes the denominator become 1 plus log base 3 of 5. Step 3. Add the two fractions by using a common denominator, which is the product of both denominators. The numerator is the sum of the cross terms. Step 4 is the product of both denominators. The numerator is the sum of the cross terms. Step 4. Expand both the numerator and the denominator. Step 5. Apply the identity log base b of a times log base I of b equals 1. Step 6. Notice the numerator and denominator are identical, so the fraction is equal to 1. Therefore, the original expression equals 1. Step 6. Notice the numerator and denominator. Show the word example, then the problem statement in orange. Log base 1 over the fourth root of 8 of the cube root of 16. Step 1. Set the expression equal to x. We'll write log base 1 over the fourth root of 8 of the cube root of 16 equals x. This is merely defining the unknown value. Step 2. Convert the logarithm to an exponential equation. The argument equals the base raised to x. So, cube root of 16 equals 1 over the fourth root of 8, all raised to the x. Step 3. Express everything with base 2. 16 is 2 to the fourth and 8 is 2 to the third. Rewrite the equation with those substitutions. And treat the reciprocal as the fourth root to the negative 1 power. Step 4. Change roots to fractional exponents. The cube root of 2 to the fourth is 2 to the 4/3, and the fourth root of 2 to the third is 2 to the 3/4. Apply these and keep the negative 1 power. Step 5. Simplify the right side using the power of a power rule. We multiply exponents to get 2 to the negative 3x over 4. Step 6. The bases are equal and positive and not 1, so we equate the exponents. 4/3 equals negative 3/4 times x. Step 7. Solve for x by multiplying both sides by negative 4/3. We obtain x equals negative 16/9. Let's state the final answer clearly. Example. In this walkthrough, we will simplify the expression. Open fraction, log base a of n times log base b of n, over log base a of n plus log base b of n, close fraction. Step 1. Apply the change of base formula. For any positive bases and arguments, log base x of y equals 1 over log base y of x. Rewrite each logarithm with base n. Step 2. Multiply the fractions in the numerator and add the fractions in the denominator using a common denominator of log base n of a times log base n of b. Step 3. Divide the complex fraction. Multiply by the reciprocal and cancel the common factor. Step 4. Use the product rule for logarithms. Log of b plus log of a equals log of ab. Step 5. Apply the change of base in reverse. 1 over log base n of ab equals log base ab of n. Recap. We converted each log. Show the example label and the problem statement. Step 1. Use the power rule of logarithms. A times log of b equals log of b to the power a. Apply it to move the factor 2 into the logarithm as an exponent on the fourth root of 6. Step 2. Square the fourth root of 6. That equals the square root of 6. Replace that part with square root of 6. Step 3. Use the quotient rule of logarithms. Log of a minus log of b equals log of a over b. Combine the two logarithms into one. Step 4. Apply the inverse property. B to the log base b of x equals x. Simplify 10 to the log base 10 of something to just that something. Step 5. Match the final form shown in the reference solution by moving the denominator under the radical. Square root of 6 divided by 2 equals the square root of 6 over 4, which is the square root of 3 over 2. Write the final simplified expression. Before we start, a quick domain reminder. So all logs are defined x must be greater than 1, and x cannot equal 1. That guarantees that log x is positive, and log of log x exists. Step 1 in the image combines the two logarithms in the numerator using the product rule. Log a plus log b equals log of a times b. Then we apply it to log 2 plus log of log x. In the image, the next line tried to turn log of 2 times log x into log of log x squared. That move is not valid because the factor 2 is inside the logarithm, not multiplied outside of a logarithm. We'll mark that as incorrect and replace it with the correct next move while keeping the same overall step position. Now, with the exponent written as log base x of 2 times log x, we can use the fundamental identity a to the log base I of b equals b. The last line in the image shows log of x squared. That is equivalent to 2 times log x by the power rule. We'll display that equivalence to match the image's final line. So, following the step order from the image and fixing the one incorrect manipulation, the simplified value of the original expression is 2 times log x, which also equals log of x squared. Here is the problem statement. We assume x and y are positive and not equal to 1. We will keep the structure identical to the source solution. Step 0. Start with the given expression exactly as written. Step 1. Apply the reciprocal identity for logarithms. 1 over log base a of b equals log base b of a. Using that on both terms gives log base square root of xy of x plus log base square root of xy of y. Step 2. Since both logs have the same base, add them using the product rule. Log base a of b plus log base a of c equals log base a of bc. That simplifies to log base square root of x y of xy. Step 3. Rewrite the square root as a 1/2 power. The square root of x y equals left parenthesis x y right parenthesis to the 1/2. So the base becomes x y to the 1/2. Step 4. Use the base exponent rule. Log base a to the k of b equals 1 over k times log base o of b. Here k equals 1/2, so we get 1 over 1/2 times log base x y of xy. Step 5. Evaluate and simplify. Log base x y of xy equals 1, and 1 divided by 1/2 equals 2. Therefore, the final value is 2. Here is the example. We want to compute the product log base a of tangent 1 degree times log base of tangent 2 degrees, and so on, all the way to log base a of tangent 89 degrees. Step 1. Recognize that somewhere in the middle of this product there is a factor with 45 degrees. I'll write a focus version that shows that term explicitly. Step 2. We evaluate that middle factor. Tangent of 45 degrees equals 1. Therefore, log base a of 1 equals 0 for any base a greater than 0 and not equal to 1. Step 3. Since one factor in a product is 0, the entire product must be 0. Read it with me. Log base of tangent 1 degree plus log base of tangent 2 degrees plus plus log base of tangent 89 degrees. Before we transform the algebra, a quick picture helps. On a number line of angles from 1 to 89 degrees, pair 1 with 89, pair 2 with 88, and notice 45 is in the middle by itself. Step 1 in the given algorithm is to combine the sum of logs into a single log of a product. The next line in the provided solution simply rewrites the same product again. Step 3 groups complementary angles together, placing 45 degrees in the middle. This matches the pairings in our diagram. Step 4 uses the complementary identity. Tangent of theta equals cotangent of 90 degrees minus theta. So tangent 89 equals cotangent 1, and tangent 88 equals cotangent 2. Step 5 applies the reciprocal identity. Tangent times cotangent 1, and tangent 88 equals cotangent 2. Step 5 applies the reciprocal identity. Tangent times cotangent equals 1. Every complementary pair becomes 1, leaving only tangent 45. Step 6 substitutes the special value. Tangent 45 equals 1. Finally, the logarithm of 1 is 0 for any positive base not equal to 1. So the value is 0. The logarithm of 1 is 0 for any positive base not equal to 1. So the value is 0. In this example, we will simplify a logarithmic expression step by step, following the classic product and quotient rules. First, here is the problem we will simplify. Then, we will apply the rules one at a time and cancel terms carefully. Step 1. Use the quotient rule on the last term. Log of a fraction equals log of the numerator minus log of the denominator. Then rewrite the expression accordingly. Step 2. Expand each fraction using the quotient rule and each product using the product rule. Apply these to every term. Step 3. Distribute the negative sign across the bracket and list all terms in a single sum. Watch for pairs that cancel. Now identify the cancellations. Log A cancels with negative log. Log B cancels with negative log B, log C with negative log C, and negative log D cancels with positive log D. The remaining terms are log x minus log y. X minus log y. Step 4. Use the quotient rule in reverse to combine the final two terms into a single logarithm. This gives the compact final form. Recap. Here is the original expression. We'll keep it on screen and then write each transformation line directly below it without changing the order of steps. Step 1. Apply the power rule of logarithms to the very first term. 3 times log base 10 of the cube root of 4 becomes log base 10 of the cube root of 4 raised to the third power. The second term is unchanged. Step 2. A cube root raised to the third power cancels, leaving just 4. The subtraction with log base 10 of 25 remains. Step 3. Use the quotient rule. The difference of logs equals the log of a quotient. This becomes log base 10 of 4 over 25. Step 4. Rewrite the fraction as a perfect square. 4 is 2 squared and 25 is 5 squared. So the fraction equals parentheses 2 over 5 close parentheses squared. Step 5. Apply the power rule again, moving the exponent 2 in front of the logarithm. We obtain 2 times log base 10 of 2/5. This is the final simplified form. Therefore, strictly following the same order and structure, the expression simplifies to 2 times log base 10 of 2/5. Step 1. Factor the argument of log 20 as 5 times 2 squared. Then substitute inside the logarithm exactly as shown. Step 2. Apply the product rule and the power rule of logarithms to expand. Step 3. Distribute log 5 across the parentheses. Step 4. Recognize the perfect square trinomial. Step 5. Combine the sum of logs into a single logarithm. Note, a minimal correction is applied here to make the expression precise. Step 6. Simplify the product inside the logarithm. Step 7. Evaluate. The common logarithm of 10 equals 1, so the square is 1. Summary. We followed the exact sequence from the provided solution, starting with factorization inside the logarithm, expanding by product and power rules, distributing, spotting the perfect square, recombining into one log, simplifying, and finally evaluating to get 1. So the square is 1. Summary. We followed the exact sequence from the provided solution, starting with factorization inside the logarithm, expanding by product and power rules, distributing, spotting the perfect square, recombining into one log, simplifying, and finally evaluating to get 1. One log, simplifying, and finally evaluating to get 1. In this example, we will evaluate the expression 10 times 100 raised to the power 1/2 log 9 minus log 2. All logarithms are base 10. First, rewrite 100 as 10 squared. This helps us keep a common base of 10. Use the power of a power rule. Multiply the exponents. 2 times 1/2 log 9 minus 2 times log 2. Now, multiply 10 by 10 to a power by adding exponents. The first 10 is 10 to the 1. Also move the 2 inside the logarithm, using the power rule, to make log 4. Replace the 1 with log 10 to prepare for combining all logarithms together. Combine the logarithms. Addition becomes multiplication and subtraction becomes division. Compute the arithmetic inside. 10 times 9 divided by 4 equals 22.5. Finally, apply the inverse property of base 10 logs. 10 to the log of x equals x. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.